see that it's inverse.
Yeah, they have volume. They tell you what.
Yeah. He did it the other way, though. Silly Nicola.
So if I do that on the test, will they get mad at me?
Yes.
Yeah.
Dang it.
Because I would have done mass over volume myself.
That's what I did. But it says plot it volume as a function of mass.
Yeah. And if they explicitly say that, then
Well,
you
live on the edge.
gotta.
You're on man.
You gotta.
Screw the man.
Yeah, stick it to the man.
Oh. Okay. So I said Bill O'Reilly. Okay. So you got your buoyant force acting up, which is going to balance out your gravitational force acting down. Now, what are the two things, as Kyle noted with the dirty dogs, what are the two things that are actually contributing to this?
What?
Good start.
There's two masses involved.
Oh!
Oh, the cup and the solid thing.
Yeah, the mass of the cup and the mass of the ball.
Sample of known mass.
Okay? Times G. Alright, that's cool. Now, quick refresher speaking of buoyancy force. Okay? What is your buoyancy force equal?
Well, funnily enough, I thought it was straight equal to the volume. It actually,
You thought it was what?
I thought it was equal to the volume. It actually equals.
You thought your buoyant force.
It actually just equals the weight of the
Weight of the
substance
volume displaced.
The weight of the fluid.
Displaced, whatever.
No, huge deal.
No, it's not.
No.
The thing that's
Kyle, you
floating-
can say it's not, it is.
The
He knows what he's talking about.
Yeah,
I don't care.
He didn't say it right, but
fluid
Okay.
thing that's in is what's displaced. It's the weight of that,
It's the weight of the fluid that's displaced.
not the volume.
Now, here's what is going to be important.
I figured that out.
When that thing sinks in, the volume that it displaces is equal to the volume of the object that whatever you put in there. I think that's what you're thinking.
Maybe.
So if you have like a 0.5 cubic meter block and you submerge it in water, that's going to displace 0.5 cubic meters of the fluid.
Yes.
But that doesn't mean that's the buoyant force.
It's not.
No, it's not. Okay, it's not.
But I fixed it, so we're good.
So it's all good?
It should be.
Okay, so then on B, derive an expression for lower flow volume. So you want to end up solving for V naught, right? So starting with this, your buoyant force equaling Fg, okay, right? So that's going to be the mass of the cup plus the mass, what is it, a ball? What is there?
It's a substance.
Oh, mass of a substance. Wow.
Yes, we're very descriptive.
Mass of a substance. We don't want to offend anyone.
It is different
Okay.
than the last.
Now, how are you going to calculate the buoyant force? How are you going to get the weight of the fluid that's displaced?
volume times density
Rho Vg.
times G
Now, which rho is that?
of oil.
The oil.
Then the
Oh, wait, what?
volume of the oil that's displaced times G. So, is the volume of the oil that's displaced the same as the volume of the cup?
No.
Not necessarily.
Not necessarily.
The cup that's submerged.
Is it equal to a portion of the volume of the cup?
Yes.
Yes. But it's not the entire cup. Okay? Because what's the only time that would equal the entire volume of the cup?
Submerged.
Yeah. And it's just filled with air. Okay? So as soon as you put oil in it, it flows. Okay, that doesn't work. So to get V naught by itself, divide by rho naught G. Conveniently, your G's are going to cancel out. Okay? You don't really want to get fancy. Now, if you look at what they gave you, because they've explicitly labeled the volume and the mass on your axes, and the volume is 10 to the negative 6th. It isn't just that number. So, here's the deal. when you find the slope of the line, what units do you end up with?
Wow.
Wow, the way they did it.
Not.
I did my graph wrong.
Meters
Meters cubed
for
over
kilograms.
Yeah, so you're gonna
Forgot
find
that
the
the
slope
cup
of this
has
line.
mass, so I just
That
started
slope
from
of that
0
line
and
is
went
actually
up.
gonna be in, well, that was
But
a
you can't
horrible
do
unit.
that
That's the answer.
Meters cubed per
because then question
kilogram,
E
because
is
you're
like, wait a
plotting
minute.
volume
cup.
here and mass here.
No, the cup is
So
float completely.
how then can you actually
It
find
has
the
some mass.
density?
So it's going to displace somewhat.
The inverse of that slope.
Right.
Yeah, then you take the inverse of that slope. Then you get, so you should get something around 750.
Haha, mine was closer. I got 800.
What'd you get?
He got 909.
Oh my
I
God.
got 888.
I mean, I did the thing.
Okay, as long, that's just it. As long as you show your work, as long as they can follow what you did, because you are drawing a best fit line. And here's the other problem, because of the fact that it's 10 to the negative 6th, because it's such a small value, if you're off, if you pick a slightly different point, that's going to play out huge in terms of that density. So then what is physical significance of the intercept of your line with the vertical axis?
That's going to give you the volume displaced by just the cup.
Yeah. That's basically it. So volume of oil displaced.
I did
Oh.
that wrong, so I just drew my line from 0.
Okay.
Whoops.
Well, it's going to be such a small amount, it's really not.
Yeah.
Okay. Speaking of work, let's go with the 2004 pressure volume graph.
The puppy is fired up.
The puppy has been fired.
Okay.
Hot dogs again? Cool.
So let's kind of start at the beginning. In the beginning, God said, earth. Okay?
It's not going to do negative work if it expands.
Now, in physics,
Yeah. I
what's
did.
your pressure measured
I
in?
did wrong.
All right, Kyle.
Wait, what? Hey. I can string coherent sentences together.
The
sometimes.
pressure,
Pascal.
force per unit
Very.
of
I
area.
changed it to that after saying per unit of volume.
Then the volume in
Volumes.
cubic meters,
Yes.
so that you, over here, you end up with perhaps Newton meters, which would perhaps be measured as joules.
Torques.
Quarks.
Now, which R are you going to use here?
8.314.
Yeah. 8.314 joules per mole Kelvin. So you got a temperature in Kelvin, you got this is in moles, right? Everything cancels out, you get joules on both sides. Life is cool. Okay. So what do you call this horizontal line? What type of action is going on there?
Isobaric.
Isobaric. Why?
Because we're keeping the pressure the same and pressure is wrong.
Yeah.
Keeping the pressure the same. So as I go across here, I'm keeping the pressure the same. But what's happening to the volume? Volume's getting bigger, okay? And then I got the same number of moles, I got the same R. So what has to happen to the temperature?
Let's go up.
Let's go up,
Which one? This one or
okay?
that
So, what am I, if you look at what's happening here, I'm going to dump energy into this thing, and the volume's going to get bigger, okay?
So,
Now,
Because
this has to go.
if you look on part A, it says calculate the work done by the gas as it expands, right? So your work is going to basically going to be this area that's underneath this graph, okay? That's it. So,
I got that one.
and this is where thermodynamics gets weird, and we've never resolved it because engineers look at it from one perspective, physicists look at it in terms of the other one. So this is the work done by the gas. And they emphasize, put big underline, by the gas. So work equals negative P delta V.
But since it's by the gas, it's gotta be.
Now, what's the only reason I can use this equation to calculate work?
Pressure is constant.
Wait, no, temperature changes, because
Don't worry about temperature. Don't leave temperature out of the question.
volume changes, but pressure stays the same.
Oh, right. Because if my pressure is changing and I have a constant volume, even that doesn't even make sense, because if I have constant volume, then there's no work done. So, because remember, you only get work when you have a change in volume. So if you do this, you get, I don't remember what you get, negative 3,600. Okay. So, remember that delta U equals two things. It equals Q plus W. It also equals 3/2 NR delta T. If there's one equation that you memorize that's, and then I always found this odd, you have to know this equation to work a lot of these problems, but it's not on the equation sheet. It's the weirdest thing. So like, this is never on the equation sheet, but probably about every 3 or 4 years, you have to know this equation to solve a problem, or it makes it easier if you do. Okay, but here's the important thing about this, in terms of a grander idea. If there's no change in temperature, guess what? There's no change in U. So, if your temperature doesn't change, U doesn't change. So, in this situation, clearly, what's got to happen to the temperature? Temperature's got to go up. So right away, I know delta U has to be a positive or negative number.
Positive.
Why?
It's going to gain energy from the
How do you know it's going to gain energy?
math.
Since volume goes up, temperature goes up because PV equals energy.
Yeah, because I'm going across here, I've got a higher temperature.
Yeah.
So my change in temperature is going to be a positive number. These two numbers can't be negative. So if I get a positive change in temperature, I get a positive delta U. So that means that the energy that I dump in as Q has to be bigger than the energy that it cost me to do the expansion.
Yeah.
Because that's the only way that delta U can be positive. So in some ways it works out to be like a logic problem. Oh, okay, right, my temperature's going up. So what did you get for this first temperature? It's like 100 and something?
108,
108?
I think. That's just.
That's what I got.
And then this one is going to be,
325.
what'd you get?
325.
325. Now, here's the other thing about these graphs. If you think about it, it's almost like a three-dimensional graph. You have a pressure and volume that's associated with every point, obviously. But the third dimension that plays into this is temperature. So your temperature is never listed, but it's like a third dimension that you can glean from any point on here. So any point on here, you can glean a pressure, you can glean a volume, there you go. And then you get a temperature out of it. So, once you get those 2 points, and this is a pretty substantial change. You're going from 108 Kelvin, which is pretty cold, up to 325. That's a pretty big temperature change. And also, you're going from 3 cubic meters to 9 cubic meters. I mean, physically, this is a big change in volume. You know, if you kind of visualize 1 cubic meter, okay, I got 3 of those, and then I'm going to go to 9 of them. That's a big, honking change in volume. Okay, so we got this action going, right? So, what'd you get for your
Honk.
A honking number.
Yeah, trust me, I know about big nose. Okay, so
You haven't seen Jeremiah though.
Huh?
You
Stop.
haven't seen Jeremiah.
Jeremiah.
Toucan.
Toucan.
That's
That's
Well, that's what. Okay. I was.
ruthless.
That's what Emma called him.
Okay, so what'd you get for delta U? It should be like 5,400, if I remember. Is that right?
Yes.
Because I've got random numbers written down. Okay.
3499.999.
So I got 5,400 joules, and then they asked you to solve for Q. Your work is negative 3,600. So therefore, your Q value is 9,000 joules.
It's not over 9,000. No.
Yep.
What?
That's a critical number.
Just memes.
Okay.
If it's over that number, you're in trouble.
All right. So here's the ramifications of this, and this is how this deal actually plays out. Let's say that you dump 9,000 joules. Let's play what if. And that's the whole key of understanding thermodynamics, is playing the what if game. What if I dump 9,000 joules of energy into the system, but I don't allow the volume to change? What's going to be my value of delta U?
That much.
It's going to be 9,000, right? So what's going to happen to the temperature change? It's going to be really, really big. Because if that happens, and I can't change the volume, all of that energy that I put in is going to go to make those air molecules inside go faster and faster and faster and faster. Oh, it's a long story, but Tuesday or Saturday I've got to go give a speech up at the Kansas Association of Teachers of Science about how I teach chemistry. Here's the first thing I'm going to say. If any of y'all ever say air molecules, I'm going to kick you out of this lecture. Okay. Air molecules. So,
Is that when you're going to talk about nature is a lazy prima donna?
that is, yeah. I'm going to drop that card too.
Wow.
Okay.
Just don't pull a Parkinson's.
Oh man, I can't believe Allie said that.
I really wanted to make her feel like a jerk because I had an uncle that died of that I loved dearly. And I almost was like, Allie, tread carefully on that. Okay. So, what if I dump 9,000 joules of energy into the system, but it does 9,000 joules of work?
Zero.
Zero. Because all the energy that goes in is going back out.
And I see that means no change in temperature.
What? I don't have my glasses on. I can't see anything. Okay.
It's a blend. I mean,
So, yeah, Q is 9,000. I'm going to dump 9,000 in. I'm going to use some of that to do work. Did you just stop it?
No.
it's on the outside.
I just turned the screen outside so we can watch what's going on.
Wow.
Oh, wait, is it upside down though?
Greg,
No.
No, what?
you're over here. Look at you.
Oh, that's amazing.
Can you see me?
Yeah, I can see you. Yeah, the old smile.
This is neat.
Isn't science great?
You gotta forgive us, Bert. We've been in this room for a little bit too long.
Oh, so have I. Welcome to my world. Okay, so we've got A, 1, 2, and 3 done. Okay, it's kind of cool. So the pressure is then reduced to 200 without changing the volume, otherwise known as ISO volumetric
I see isometric.
Or metric.
or isometric, either one. Okay, from state B to state C. So what's that look like on your graph? What are you going to do? Draw a line.
Boop, boop.
Straight down?
Yes.
Okay. So some action like this. So here's C. How much work is done? None. Why?
The volume didn't change.
The volume didn't change. Okay. You can't use negative P delta V if you wanted to. Well, you could, but you just get 0. So here's the deal. Physically, what would you have to do? So again, look at this line. If you're going down like this, start with PV equals nRT. As you go down from here to here, what happens to the volume? Stays the same. All right, I got a constant volume. What happens to the pressure? It drops. I can't change N or R, so therefore I have to drop the temperature. So physically, what would you do to this system? You'd have to do two things to make this happen. Kyle, what's one of them?
Lower the temperature.
Lower the temperature by doing what?
Releasing it.
Release. I bid you to
Releasing
leave.
it. Go, fly, be free.
Yes.
If you love something, let it go. It will cool down.
Just ring a bell. School's out. You can leave now.
Just stick it in a little freezer.
Yeah, or an ice bath or something. Okay?
So remove it. There you go. That's how it's like.
Yeah.
It's like
Okay?
Wait until winter.
Now, what's the other thing that you would physically have to do to this if this was a syringe?
Lock the sorry.
Yeah, you'd have to lock it in place so the volume couldn't change. Okay? You would have to physically change the structure, whether it's a sliding piston or something, so that when this happens, you're going to drop the temperature and your pressure is going to go down. Now, in this situation, as this goes down, are you necessarily decreasing the number of collisions? Because what at the heart and soul of this, what creates pressure? Okay, what does this mean? Trout?
That's not fair, right?
How fast they're like hitting the side.
Yeah, and how
How
much
many
force
times?
they're hitting him with,
Yeah.
right? So to drop that pressure, I can do one of two things, or a combination. I could decrease the kinetic energy of the particles, which would be reflected by dropping the temperature, or I could decrease the number of collisions. So as these things slow down, okay, I'm probably doing both. They're not going to have as much kinetic energy, and I'm not going to be having as much collisions. Okay. So we got that one. So then we got C, the gas is then compressed isothermally back to state A. Draw a line or curve on the diagram to represent this process. So what's that going to look like?
Because
Straight line?
it's like,
No,
no,
curved.
But like
that?
curves
other
The
way.
other one. The other
No,
one. The bottom.
Because
The bottom.
it's inverse, so if you go P as a
Oh,
Y,
what's an
it's
inverse?
1 over V if V were the thingamajig, so it's like Y equals 1 over X. So it's a zoop, zoop.
Okay, let's talk a little bit more savory.
That's pretty common.
What are you
As opposed
talking
to-
about, Bird? That was a perfect explanation.
I don't even know how you spelled that on the test. Because of zoop. Okay, what's going to happen to my NERT?
Nothing.
Nothing. It's an isothermal. The temperature isn't changing. As I go from here to here, what's happening to my volume? It's going down. So therefore, the pressure has to go up. Okay? It's cool with this. Now, when I went from here to here, what was the sign of my work? Positive or negative? Negative. It was doing negative work coming across like this.
So it must be positive.
So going that way, that's going to be positive work. Now, can you use negative P delta V on this line?
I don't think so.
No. This is where you've got to use that NR natural log. No, it's NRT natural log V1 over V2, something like that. That. I've never seen you actually have to use that on the test. Okay? Just know the concept. But here's the bigger idea. If you were to compare the work in compressing it isobarically versus the work done in compressing it isothermally, just in magnitude alone, which one is going to be more work? Why?
Bigger area.
Bigger area. You just look at the graph and go, oh, there's a bigger area. Okay, right. Spot on. Here we go. Okay, so going this way, the work is going to have a positive sign, so therefore Q has to have a
Negative sign.
Y.
Because temperature doesn't change, so
Therefore,
delta U is 0.
is 0. So,
Q equals negative W.
yes. So basically, you're going to have positive work, so you've got to have an equal and opposite value of Q. So if Q is negative, what's going to happen to the system? we're going to remove energy. Okay. All right, we're in the home stretch. So let's try the projectile motion problem, which is kind of cool. So,
ball images.
the 2013, number 4. So, Sam,
Oh, this one.
let's do the Emma. Okay, so let's start with A. So how are you going to do A? What's your overriding theme to do A? What happens in the
X.
stays in the X, and what happens in the Y stays in the
Lemmings.
Y, right? So, what's the only thing that's going to determine how long this ball is in the air?
Horizontal velocity.
How velocity is going to determine how long it's in the air.
Well, yes, if it's
Brilliant.
perpendicular.
You have
Using
been
the
my student
right-hand
now for
rule.
almost 9 months.
See, Berkham, if you use the right-hand rule for the velocity of the ball in the direction
It's
of the
too late to
gravitational
abort.
field,
Yeah, okay, it's a proton
9
that's
months.
launched in a magnetic field that's going into the page that's creating a downward force. Gravity is just electricity.
And
Okay.
there you go. Right-hand rule every time.
Arrowhead rule.
Okay,
Honestly, everything will suck.
so basically, you're going to work off the idea that distance traveled is equal to velocity times time. Why can you use this horizontally?
It's constant.
Yes, we're assuming that there's no horizontal forces, inertia rules, Newton's first law, boom, here we go. Okay. So, how are you going to get the time? Where's that equation going to come from?
The X doesn't have any.
Yeah, that one.
Yeah, x equals 1/2 at squared plus v naught time. Do you have to worry about this? No, it has a velocity.
But not downward, which is what I care
Yeah,
about.
because what happens in the x stays in the x. So if you're going to use 9.8 meters per second squared here, this is going to drop out. So, you know the distance that it's going to travel, which is the 1.8. You can find the time it's going to take using 2x over a, the square root of that is time. And you should get 2.6 meters per second. Got it with that.
That's where we went wrong.
I think by we, I think you mean you.
That's not where we went wrong.
I got that.
Okay? So this thing is traveling at 2.6.
I went wrong a
You got
lot on those.
2.9. What the heck?
Just ignore those.
I actually get
I
2.9.
don't know.
Did you forget to take the square root of 2y over g?
Okay, you get 2.6. You're under there. Now, at this point, what do you want to calculate? The acceleration, right? Okay? So what are you going to use there?
That equation.
That equation. So now you got to use the 2.6 that you just found. You should get an acceleration of about 3.6 meters per second squared.
Well, hold on there.
It's because we used like 2.5.
I use 2.57.
You know what?
Wait,
I used 1.8
That's
instead
still-
of 2.4. That's what I did wrong.
that still doesn't get you 6. Wait, 3.6?
3.6.
3.6, okay, yeah.
Yeah,
If
3.6,
you use-
not 6.
If you
you
used
don't
2.6 instead of 2.5, yeah, if we didn't round, so we got 4.24 as the
Okay.
master block at the end.
Okay, that,
Because like our acceleration is 3.48.
Yeah, that's what mine was.
oh, I just kept it at 2.6, not 3.6.
Okay.
Okay, all right, so that was that. Okay.
Don't round until the end, kids.
Well, but also, this is why you show your work, so if there is a discrepancy, they can look back and see exactly what you did.
I
So
showed my work.
you can keep the numbers in your calculator, but write them down, you know, like at each step, so that again, you have to get yourself in the mindset of the grader. These graders want to give you points. That's what they want to do. But they can only give you points for what you show and the equations that you show. So make sure that you write stuff down, okay? All right, now here's the big kicker. The toughest part conceptually is what's going to happen on C.
Those papers aren't very good.
So here's the deal. So here's your table, here's the mass, boom, boom, boom. And this is this 2.5?
Yes.
Okay. So here's the kicker. What's the only thing that's going to make the mass accelerate?
The downward force of gravity.
This. This is going to be your net force. There's no opposing forces. There's no friction. Nothing. Is the gravity pulling down here? Yeah. But guess what? That's balanced out by your normal force. Okay, cool. So, the only gain in town is going to be this 2.5 kilograms times g. That's going to be your force, right? Now, over here you're going to use ma. At this point you know your acceleration. Cool. But what do you use for the mass?
Total mass.
You have to use the entire mass of the system. Okay? Just not the mass that's up there, just not the 2.5. It has to be the entire mass of the system. So you get 2.5, what's that one up there, 0.3? And then plus x times 3.6 meters per second squared. So for x, and you should get around 4. Luke, did you see where things went south?
Yeah, I just didn't do. I got everything right until like the mass of the hanging mass as well.
Well, you
Okay.
see, I use the horizontal.
All right, so to finish up quickly, let's try the multiple choice questions.
All of them.
Yeah, all of them. There's only
Maybe a couple.
7 multiple choice questions.
Was actually 8.
Sam. Smoker's cough. Okay. So, let's talk this question. What do A and B have in common?
Not moving.
Okay, if they're not moving.
B not equals 0.
Okay.
What's what not moving means?
So,
D.
but what else do they have in
I
common?
didn't even read
There's
B.
a
Same mass.
Yeah, genius.
Okay. What else do they have in common?
They're in the same gravitational field.
Good.
So therefore they have the same
Attaboy.
UG, right?
They're on the same planet.
I guess.
Since they have the same UG, guess what? Whether you fall down like this, assuming this is frictionless, all you have up here is UG. So when you get to the bottom, all that UG changes into kinetic. So does it make any difference if this one slides down?
Not really.
Not with final speed.
No. Okay? It's not going to alter anything. So both of these land with the same speed. But does this one take the same amount of time to get down?
No.
No. Why?
Because the acceleration is g sine theta.
Yes, the acceleration is much less, but I'm going to take more time, but I'm going to end up with the same speed. Now, let's talk this one. Why doesn't this one land as the same speed as the other ones?
Because it starts with some kinetic energy as well.
It has UG and KT. But when it lands, it only has KT, but this KT has to be bigger than these KTs. So therefore, with all that said, the answer to 5 is
B.
B, and the answer to 6 is
C.
C. Beautiful.
Wow.
7. Kyle, what do you have for number 7?
I put down C.
I think you would be correct. Why can't it be D?
Because can't read.
Okay.
Mostly because energy is conserved, so that way if it goes up.
If energy is conserved, then why isn't the answer 10?
Because it bounces up to 7 joules. So.
So where did the 3 joules go?
I don't know, probably the collision.
Yeah. Okay. It bounced. We vibrated. It made some sound. Okay. So the whole key to wording this, and sometimes they get weird about this. It's got the ball, earth, floor system.
See, when I saw that, I just assumed that it meant like everything. So it was like, and that's a pretty broad generalization.
But then it says, what's the mechanical
This is
energy?
not the universe.
So the mechanical energy is just the energy of motion,
Okay.
The
so
ball,
it's-
earth, floor, universe system.
Okay.
of entropy. Okay.
Oh no.
So you're right. The answer is C. Now on 8, what does 8 technically involve? 8 technically involves a whole bunch of things.
Torque.
Torque. It also involves
Angular stuff.
angular stuff. Let's define angular stuff.
But
Velocity.
Angular momentum,
fish.
Button fish.
but fish and
Theta.
alpha. Well, that's alpha. And theta, right? So, does the wheel want to slow down?
Yes.
No, it doesn't.
No, but
No.
it will.
Wheel wants to
slow
keep
down.
spinning at a constant rate.
Yes.
So therefore, to change it and make it speed up or slow down,
Some stuff.
Neither.
Mass. Hanging mass.
yes. Okay? So is the hanging mass going to create a torque?
Yes.
Yeah.
Yes.
Yes. What two things does torque equal?
I alpha.
Fr and I fish, right? So in this case, you're applying a torque to the outside, right? So which one's going to create more torque, the 40 Newton force or the 20 Newton force? 40, because torque equals
For
Yeah, the same radius.
Fr, same radius, therefore with a greater force you get more torque. Leading to the correct choice then of number 8 to be
C.
C. Because it's going to start off with the positive but not. Which just is fun to say. Okay. 13. Now, this is a center of mass problem. Let me give you the hidden key to this problem. So, start with the beginning. So here's the platform, here's the swimmer, right? They both have equal mass. So where's the center of mass in the system?
It's like there.
Right.
Right there.
It's a little to the right of
Yeah,
the
right there.
end of
Here?
the line.
Okay? Here.
More or less.
Now, so when he starts to walk this way, what's this thing going to do? It's going to go back that
It's
way.
gonna
What
launch
do you
back
think
that way.
happens to the center of mass if there's no external forces occurring?
Stays the same.
Stays in the same place. So if you can figure out where the center of mass is, that's where the center of mass stays. So what happens in the center of mass stays in the center of mass. So that leaves you with an answer then of
C.
C,
All these C's.
because that's where the center of mass stays. So help
5
me.
C's in a row.
Yeah. So help me if any of you missed number 14.
A.
Good Lord.
I plus I2 equals I. No, there's a better answer on 15.
How about 14 is D? Okay.
15 is also D. The best answer.
God, I love
my
making
favorite.
nerd jokes. This is great.
Okay, so 15, oddly enough, is
C.
C.
C, because they're both inverse square laws. Okay?
Number 16 is dumb.
Well, let me explain the hidden meaning of 16, because there's a whole bunch of weird things that happen on 16. So first off, they're combining momentum and this concept of uncertainty in measurement. Okay? So if you look, first off, it's a momentum problem. Because you've got A and B that are of equal mass, they're going to hit, they're going to do the California thing and move off together. Okay? So if this thing is moving at 3 meters per second, now here's the deal. Here's the hidden meaning of what information they give you. It's moving at 3 meters per second with an uncertainty of plus or minus 0.2 meters per second. So that uncertainty is only in terms of the measurement before the collision. So if you have an uncertainty of plus or minus 0.2, what do you think that velocity can be between?
2.8 and 3.2.
Yeah, so it's going to be somewhere between 2.8 and 3.2. And in reality, as evident by your force labs with the magnet, there is some uncertainty in measurements. Okay? It's the nature of it. All we're trying to do is minimize the uncertainty in the measurement. So, since this can be plus or from 2.8 to 3.2, after the collision, what's going to happen to these velocities? Since the mass is going to double.
Half.
Half. So that's going to be 1.4 to 1.6. Here's the hidden thing. they didn't mention any uncertainty after the collision. So since the uncertainty is only known before the collision, that's what you have to roll with after the collision. Go home. And, yeah, shut that down.